Hello. So I'm going to show you a demonstration of the assignment one, building a grid lattice discretized space representation of a little simplified game environment. So I'm going to switch over to Unity and show you the starter project, and then I'm going to give a demonstration of my implementation. So I'm going to show without the little portrait so that you can see all of Unity. All right, so if you go to the link that's on Canvas and clone or download the project and then open in Unity, you will probably see a view something like this. Often when you first clone a Unity project and open it, uh, there will not be any scene open. It'll just create a default scene. So you might be wondering where everything is. So in this case, you want to go to Assets and then look under Scenes. So if you go to Scenes, you will see Grid Navigation, Nav Mesh, and Path Network. So the first assignment you're working on is Grid Navigation. So you want to open that one up. You'll see something like this. And then you can, if you want to immediately try it out, you can hit play. And here is a demonstration of it running. And you'll notice it's not working as you might expect because it's not implemented yet. So you'll see that there is a scene, there is a polygon here. You can click it and you can drag it and place it in different places. You'll notice there is this ball here. That is our agent representation. And you'll notice a green outline there. And so that's a cell of a grid. It's an incomplete grid. It should be extending the full extent of the game world canvas, but it's not. And you can click places and path planning will be attempted. And right now it's not really that compelling because there's only the one grid cell. So it doesn't really even make much sense what's going on, but you can see this ball moving around. And so another feature I want to show you is you can switch between scenes. So I think it's 1 through 7 currently. So just jumping around. So these are the different scenes that you will need to make sure that your code works with as part of your testing. So yeah, I ended at 7 there. So there's several different scenes. And there's some features that'll be of use. Maybe I'll go through them right now, and we'll check them out again in a bit. But one thing that you'll find is useful is to toggle on and off the drawing of the polygons. You can still see their outline, but if you hit T for toggle, you can see that we now only see an outline. Well, we can't, I don't believe we can drag them anymore. Yeah, so no, it still drags, you just don't see a visual update. But yeah, you can toggle them back on and then off. And so the idea is that you can see underneath. So if there's a grid that's filled out, you can tell whether the cells are marked appropriately. Let's see what else is important. I think some of the things we'll have to wait for. I will go ahead and point out that you can hit spacebar to change your search strategy for the path planning. That's something you might want to play around with. Let's see. Another one is there's V, which right now is not going to do anything. We'll see another full implementation in a second where this will make sense. But you can hit V, and so that triggered a reload of the scene. But when you hit V, what that's doing is toggling on and off visibility of the graph that you're going to build from your grid. So the graph would be nodes and edges, and the grid is looks like a checkerboard. But superimposed on top of your grid will be that, and then you can change for each of the maps 1 through 7. If I toggle through, so each of these you can switch between 4-way and 8-way connectivity by hitting the period on the keyboard. And by the way, let's see, if I go to, that would be on the agent sphere. Actually, sorry, I think that's on the navigation area, rather. I think that's where this setting is. Game grid. All right. This may be difficult to see, but so the game is still running, and I'm looking at the hierarchy view. I selected the navigation area. A lot of this, you don't need to understand all the functionality in the entire application. But I did want to point out that the grid connectivity, when I hit on the keyboard, I hit the period, hopefully you can see over here, I know it's probably really tiny on the video capture, but it says grid connectivity, and every time I hit period have the focus on the game, you'll see 4-way and 8-way switch the connectivity on the grid. So there's just some code handling the key press that's built down into the system for handling that. So if you've read the assignment description, then you know that what you're going to attempt to be doing is fill out the grid such that rather than just being a single cell, it fills out all the way across the width and height of the canvas, as big as it can go with while staying just under the inside. So it might be a perfect multiple, the dimensions, or you might be slightly under in terms of the integer size of cells. And it would have a little bit of overhang from the game world that's not discretized. And then wherever there are these obstacles, such as the star or these rectangular shapes, if that overlaps any part of a cell, then that cell would be marked untraversable. All the other cells would be traversable. So that's your objective. I'm going to drag over the code real quick in Visual Studio. So I'm going to show some of the code here. And so actually I'll switch back to Unity. So you can get to the code within the Unity browser under the project. You'll see that there's a scripts folder, and then all the work that you will be doing and the work that you submit is under Game AI Student Work folder, and the first assignment is grid navigation. So it's this create grid file that you want to open. So we'll just already had it open. We should just switch back to it. So it's in this file that you will be implementing your code. You will see that at the top there are some helper methods. Well, first of all, there is a student author name. I want to make sure and point out that you edit this and type in your name. And then there's some helper methods. This is point inside polygon, convert, intersects, and then you get to some code that you have to implement. And you'll see these to-do implements. So you'll need to implement a method for testing whether a point is inside a bounding box. So you have these vector2 ints, either vector2s that have integers for the terms in the structure. So the minimum cell bounds and the maximum cell bounds, and then the test point that you're testing. And then there's a description here of the test that you're implementing. Is traversable. And so this is given a grid with, it's 2D grid with indices X and Y. Can you traverse from the given XY cell in traverse direction? And traverse direction is an enum. So we can go to the definition, and we will see that it is listed here. So traverse direction. And so this is in the traverse direction CS file. So we have up, down, left, right, up, left, up, right, down, right. And then there's also, you'll see grid connectivity there, 4-way and 8-way. And so, of course, some of these directions would only apply if 8-way is enabled. Otherwise, 4-way would only use the first 4. So go back. Oh, sorry, that is the test code. We'll talk about that in a second. So is traversable. So the is traversable is actually how the grid that is created ends up being used, is you need to be able to refer to a given cell and then analyze based on neighboring cells whether it's possible to go in a direction or not. And you can use that code that's implemented, this is traversable, recommended to use for this create path network from grid. So this is sort of an academic exercise to demonstrate that that you understand how the grid relates to different world positions, how it relates to grid structure, and it also happens to be the way that all the path planning code relies on a path network or a graph, and the graph consisting of nodes and edges. That is needed for the path planning part of the project. So even though you could have it operate, you could have path planning operate directly on the grid using only something like is traversable method here. Everything is standardized on a grid, or sorry, a graph. And then probably the most important method that you implement is create. And so this is actually where everything starts. These other methods that we've looked at so far are really in support of create, or the output of create. So when a scene loads, create is called. It passes you the origin, which is the bottom left corner of the navigable region, and it's in the world coordinates. This position is not going to be 0, 0. It can be anything. Then you have your canvas width and canvas height. And it doesn't say it, but those will always be positive. Then you have your cell width. That's how big you want your cell to be. And so with that information, that determines how many cells you could possibly span across the width and height. There are a list of polygons, which are just the list of vertices. These can be concave polygons, and you get the counterclockwise list of the vertices. So the polygon is a class, so you can call get points or get integer points to access the data of the polygon. Then you'll notice there's an out parameter for the grid. So that's the actual grid that you are going to return. So there's a little bit of code provided for you to show you how to instantiate a grid with some dimensions. Right now, it's just dimensions of 1 by 1, but you could pass different dimensions there. So grid equals new bool. Our grid is a set of Boolean values, and that will represent for each grid cell in the grid lattice. It is true for traversable, false for not traversable. And let's see, is there anything else I wanted to cover here? So yeah, you're gonna implement this code. You're gonna make the grid, then you're going to work your way through all the cells of the grid, testing against your list of polygons. You'll definitely want to check out the Intro to Path Planning lecture and Grid Lattice, where these all the scenarios, the different sort of geometric tests necessary will be covered. Values that are in the game world coordinates or dimensions, such as the canvas origin, canvas width, and canvas height, can be converted with, if you recall, there's the convert method. Of course, the width and height you will need to put into a vector 2 in order to use this convert. So like canvas width can be the x of the vector 2, and canvas height can be the y. And let's see if there's anything else. I guess next up, we'll look at the presets. If you want to know how to get to the presets, let me go back to Unity. All right. So if you go in, again into the project view assets, you will see that there is a scripts config folder. So if you go in there, that's where you find the custom preset config. These are all the configurations that I provide to you. There's a few more numbers on the keypad, so you can use 8, 9, and 0. And those will automatically map for you if you create more of these. So if you do make a new one, I would recommend you make just cut and paste one of these methods, such as sc0 for scene config 0 and so on. They just keep repeating. They're all cut and pasted and modified basically. So if you added new ones, you would add additional lines here and say you would make cut and paste sc6, then you'd make sc7, and then you could work from there. And these configs, you'll see they set up information related to the scene. So we have an origin, we have our obstacle configs, and if you look at the constructor for the obstacle configs, you'll see that it takes an obstacle type, which is an enumerated value, a position, a scale, and a rotation. And then the way this code is written, all the obstacles are offsets from an origin. This just made it easier for me to make test cases, but you could skip that step and just directly set the true positions that you want. Then these path node positions have to be provided, but you can just leave it empty or just cut and paste from another example and ignore them for this assignment. That's for the path node positions would be used for the next assignment. And then there's a scene config, and you can read through the constructor with the IntelliSense here, and you'll see scene config takes the origin, the world size, the origin, agent position, agent scale. So that is the ball that rolls around. Then you pass the obstacle configuration, the path nodes, grid cell size, and then there's this num extra path nodes and int seed. Those you can just ignore you can pass a value, but you can just replicate something you see in one of these examples. So just pass zero and any seed, and then you don't have to worry about it. But that allows you to set up different objects and to make visual test cases. Now there's another way to test your code. Go back to Unity again. And if you go back to the Game AI Student Work folder where I said all the work that you will be performing is, and then again, the create grid file is under grid creation, grid navigation. Then look under tests. And so under tests, you'll see that there's a whole bunch of these test files. And so the one that you would potentially be interested in is grid test. You open this file and you'll see that there are a bunch of tests. And these are unit and integration tests. And so if you just read through, there's a bunch of descriptions that describe some of the basics of writing these tests. But you can see that a lot of the tests consist of assertions. So like assert that grid is not null, and so on. And so there's one test to see if your code, once you implement it properly, creates an empty grid. And here's where it actually calls. Since you're implementing a static method, a static public method, you can call it just from the name of the static class, create grid.create. And you can also do the same thing with your create path network from grid. And yeah, so you build out some tests. I just gave you a little starting point, but it is good practice to create tests, especially as you're writing your code. If you add new features, you want to make sure old things you implemented continue to work. So this is a really good way. It lacks the visual feedback of using the custom preset config. So I kind of recommend using both approaches. But those are the three files that you're most likely to be interacting with. For the most part, you'll be staying in this create grid CS file. All right, so next up, I'm going to have a little jump cut intermission, and I'm going to show you my working code. Okay, I am back, and I realized that I wanted to show you how to actually run the tests before we move on to my example. So I'm going to actually do that first. So the test runner is built into the Unity IDE. So if you go to Window, General, and then Test Runner, you'll get this window, which you can dock somewhere. And under the test runner, you'll see a whole bunch of tests that have been picked up after they were compiled. The grid test is the one you're interested in. So that's the file that I had just shown you with the test. So if you run that, run selected, you can see the test run. And you'll notice that the test empty grid actually passes, and that's because the test is kind of incompletely implemented. Technically, it is an empty grid, but it's not a grid that fills up the canvas in the test. But you'll see that it does fail test name, and you can click on it and read the text, which is probably too tiny to read right now, but it says you forgot to change your name, and it says expected name string containing, or expected to not have a string containing George P. Burdell, because that's the default string. So that the tests are generally pretty descriptive. It automatically builds out the text for much of what gets printed. So yeah, that's how you run your tests. It allows for some pretty efficient development if you embrace testing like this. All right, so next up, I am going to switch over to my implementation. Get the window here. I think I got it. Yeah. All right, so I'm going to run now the code. So now you notice, well, one I set maximize on play, so it'd fill up the screen. The grid is now filled, and so that means the grid's fully implemented, and the path planning can now be performed. I can click in different locations, and right now it's in breadth first search mode. I can switch it. Go ahead and jump to A star. So here you can see it's a more efficient search. I can jump between the different configurations. So here is the second one. It's a much coarser grid here, but the blue is marking untraversable and otherwise empty. It shows where the traversable part of the map is. And recall I told you about the T key you can hit. So I can look underneath and make sure that every single cell hidden underneath those obstacles are in fact marked as untraversable. That is the case. Next up, I want to check out visibility. Toggle visibility of the graph. And so here we see that the white lines show a four-way connected graph based on the grid. And so it gets a little confusing looking at all these lines, but you see that the white lines intersect. So any of the points that are intersections of the white lines, those are nodes. Now there's occasionally you can't tell for sure that there's nodes, like where I'm moving my mouse cursor. So that little area is somewhat ambiguous, but otherwise I think this is a pretty good visualization. And then if I switch to 8-way connectivity by hitting the period, so it's going to stay the same scene unless I drag something around. Actually, I'll go ahead and do that. I'll drag something. You see it updates. But if I hit the period, if I change the connectivity, it'll trigger a reload and move the geometry back to where whatever the preset is at. So now you can see it's a very different pattern because we have the 8-way connectivity. But so you can see how the graph that is created by the grid can be generated here. And we can check that out on different scenes that we load. Here's a very busy one because of the grid size. This is one that I used in the videos about the like the searching. I'll often use this particular scene. Let's see, let me turn that off. You can see the how the path search works. And just for fun, I will. Whoops, sorry, I hit tab by accident. That is to switch between the different scenes for all the homeworks. That was so homework 2 and 4 were shown, and then 3 is path search. But I'm back again and hitting the correct button. So yeah, I meant to hit spacebar. Wanted to go to the random depth first search, and then if you right click, you'll do an incremental search. Right now, there's a little time pause, so it goes really slowly. That's not a reflection of the efficiency of the algorithm. Like it's normally instant. So if I click like right now, you'll see it's really quick. Even though depth first search is not an efficient search by any means, just on this particular scene, it's still pretty quick. And so yeah, you can see things moving around. Of course, the search isn't part of the assignment, but it can be a demonstration of that your additional demonstration that you've set up your grid and the graph that you form from your grid are all functioning. But probably more effective is to look at the visualizations. Oh, and by the way, if you click on the screen and get a bunch of stuff you want to go away, you can hit C for clear. And so I'll go back to viewing the connections here, and I'll toggle just to see how the algorithm has marked all of these cells as untraversable and all the connections there. This is for 4-way. I think I was on 5. Let's see. All right, 4, 5. Look under there. And then there's 6. So this is one definitely the toggle is useful. You can see under right there. And then there is 7 here. I think that is all of them. So next up, I'm going to stop this. I'm going to make a little change here. Hopefully, if I did this right, I'm going to show something. I just got to type in a little bit off screen here. But I want to show what happens with the visualizations of your graph if you don't get all your edges made. Hopefully this works. Let's see if I did it right. There we go. So I introduced an error in my code, and hopefully you see all the red lines. That is demonstrating that I have edges connecting, say, from so we're in the middle of the grid cell here with my mouse cursor. This edge going down to the next node below exists, but the edge going back up does not exist, or vice versa. So you might, well, you can't tell just from the color. You just know that you have a mistake. If you see red, then that demonstrates the mistake. See if I can introduce another little problem here. Okay, I implemented another intentional bug here. I'll show you something else to look out for and what it might look like if it occurs. So have a correct grid generating, but again, the problem with the graph generated from the grid. So I toggle on the view. You'll see that the the graph, each of the nodes are off in terms of where they should be, and so that's reflected by the shape that is created here. So clearly, these are out of bounds. So this is a sort of a common bug I've seen with this assignment, that students will like be off by once. They have some of the nodes hanging off on the side here, perhaps, but otherwise be correct. So that's something to look out for, and it helps to use the V command to check it out. So yeah, I think that covers probably everything, at least to get you started. Hello. In this video, I'm going to demonstrate the path network assignment. So let me switch over to Unity here. So this is the starter project. Of course, to work on the path network assignment, you'll be working with a new scene. So under scenes, you want to open path network, and then you can hit play right away, and you'll see nodes, but no edges connecting the nodes. So your objective is to figure out how to connect the nodes, and the requirements are that none of the edges can be too close to anything such that the agent is unable to traverse along the edges. So you can actually think of each edge like an extruded circle. So you stretch a circle and it makes something that looks like a tic-tac sort of shape. So that would mean that a node can't be too close to the boundary edges. And by the way, for visualization purposes, the nodes are the same size as the agent. So you can see how, if I can get it just right, takes up exactly that size. So if you ever see something like a node overlapping a boundary edge of the game level, then you'd know that, well, right away, the agent cannot be in that location. Similarly, with obstacles, the node, if it overlaps or is underneath an obstacle, well, the agent cannot be there. So any edge that you would connect with a node that's overlapping with something is clearly disallowed. So if you're thinking about making an edge where I'm showing the mouse cursor, well, that's not allowed because of this node. But you also have another situation that you'll be concerning yourself with, and that is if the corridor, so if you make this line, you want to make sure that it's clear. So you're considering this node, or I'm mousing over, and this node. Well, if you draw a corridor that is the width of the agent, it would clearly clip this corner here of our one obstacle. So it would not be allowed. and I will jump through some of the different predefined scenes here in a second. But you'll notice you can click around, and the clicking just identifies the nearest node that's got a line of sight with the mouse click. Of course, if it's not connected, the agent can't get there. So right now, it's not really a useful graph search, but it is trying to work. It just needs some edges. All right, so we're on the first scene. I'm going to jump to 2, 3, 4, 5, 6, 7. All of them have different sizes and configurations here. I recommend 7 is probably the most useful for debugging this assignment. So next up, I'll show you a working example. Well, actually, let me show you the template code real quick before I do that. So this is the code that you're going to be expecting to modify. As usual, change the student name to be your own name. The autograder does check that. You have some methods that are useful for completing this. So the conversion for integer discretization of the space. You have a call to intersects, and you have distance to line segment. And let's see what else here. All right, and then the create method. This is where you're going to do all your work. So you'll notice you have out parameters, or just out parameter for path edges. You're given the path nodes. You don't have to create that. You're given the nodes, which you're seeing visualized on the screen, and then you've got the path edges. So that is what you're building. And here, I already have the initialization for you, creating the list of size. It's got to match the same number of the path nodes, and then just filling each of those. The inner list is empty, so it's a list of ints, and those ints being references to an index into path nodes. So if we're looking at the 0 entry in the path edges, that coincides with the 0 entry in the path nodes. And then if that 0 entry in path edges, the list that it contains references nodes like 1 or 2 or 3, then that means you go into the path nodes to that index 1, 2, or 3, and then you know which node it's pointing to. So it's the same structure as you saw when you were creating your graph for assignment 1, but in this case we're using it for the purpose of making the path network. So you need to go through analyzing especially the boundaries of the canvas. So you will leverage the origin and the width and height. You will also use the obstacles, iterate through the obstacles, and then look at each obstacle's the edges that make up the obstacle. And you'll need to use the agent radius to understand the relationship between the candidate path edges that you might be forming and the distance that it needs to be from the obstacles or the boundary. And again, you're going to want to use the provided methods, especially intersects and distance to line segment. All right, and let's see. So next, I guess I will show my code running. Here is a reference implementation. You can see here that these edges in white were all formed successfully, but if something gets into the corridor, it goes away. If the node gets to the point that it intersects with the boundary, it disappears. Goes outside, it doesn't work. Touches an obstacle, doesn't work. And if the corridor is intruded upon, it will not be allowed. And once you have some nodes, you can then perform your path planning. This is with breadth first search, but you could try the others. And again, keep in mind you have not implemented a star, which also means that greedy best first search and Dijkstra's do not work either because they are built off of a star. So that's 1. Go to 2. Some of these get rather busy looking with the number of nodes. 3, 4, 5, 6, and 7. And this is, I think this one demonstrates all of the different possibilities for ways in which you can set up your test using those the methods that are provided at the top of the file. I think like some of these that fail, for instance, so say this node and that node are blocked by edges of this obstacle. Let's see, these are blocked as well. This one is too close to an obstacle. This one's too close to a boundary. So I think that demonstrates all of the different sorts of tests you'd want to do. So yeah, I think there's probably less work in this assignment as compared to the grid lattice. If you're having any trouble with the assignment, definitely encourage going back and checking out the lecture where the path networks are discussed. I have a slide that's kind of similar to this, but with a bit more information that I go into. So be sure and check that out as you're implementing your code. And if you have any questions, feel free to reach out on Piazza. Hello, I'm going to give a demonstration of my NavMesh implementation for assignment 4. All right, so I'm going to start up straight into the running version. So here is a calculated NavMesh for configuration 1. So I can drag the obstacle around. So one thing you'll notice is that there is yellow everywhere. So offset by the radius of the agent along the border of the world or canvas. And then we have radius offset, approximately a radius offset with the blue line around all the obstacles. So this scene only has one. So you can see there's the radius offset. So from those offset positions, everything should be filled in with yellow, and all of these triangles, probably doesn't show up on the video too well, very thin blue lines for triangles. And then these triangles have been merged. So some of these, while everything looks like almost a triangle, some of these are like kind of trapezoidal shapes. I think this guy right here is got a little extra fourth side. A few other places I think that is occurring. But yeah, you can drag this, whoops, you can path plan on the path, and there you don't have to work as long as you're picking the centroid or center of mass for the triangles. You don't have to worry like if somehow you end up clipping a corner or that sort of thing, that there's not guaranteed validity in the movement by picking the center of the triangles. But as long as it's clearly in the center of the triangle and that they're connected. So something you're looking for is that if there's, say, an obstacle that's not up against a wall, there should be a path around it, and so that should be observed through the path you see and like where you click. So I should be able to click and go around that way, and then click and go around this way as well, as long as I can make a circuit. Sometimes it's hard to see if there truly is a circuit there. So one thing you can do is just do the clicking for the path planning around it. It's good to, let me clear that. So you can hit C to clear, but it's good to try to move your obstacle around and just make sure that as you move around, you're still getting the loop around it. Of course, if you go all the way to the edge or where you intersect the expanded boundary, you can't go around that because there's not enough room between, but you slowly move out. You should be able to make just a little sliver, and then as soon as there's a sliver, it will fit through, as you can see there. So we're still in the first configuration. I'll go to 2. And you can see this one's much more complicated. But again, you might want to look for, just make sure you can go around everywhere. It'd probably help if I switched to A star. So I made it around that way, and then I should be able to go through the middle here. And I'll see if I can pass through this one. That ledge, or edge, I mean, and then go around the other side. So it looks like that one's all good. Again, you can move stuff around. So I guess I'll go to the next one. So here's another example. Kind of a tight fit here, but it does fit. And again, we can look to see if we can go around. Yeah, that is fully connected. Fit through there. Oh, and this would be a good time to demonstrate that you can end up with holes. So this is already handled in the code, or at least it should be. So there's a library called Clipper that's being called, and it's actually doing the expanding and joining of the geometry. That's an incredibly hard step. There is a very difficult algorithm to deal with some of those sort of operations that is well beyond the scope of this class. So I just used the Clipper library, which is well regarded for doing this sort of thing. But there should actually be a little bit of, I guess, a border of the obstacle here in the form of a hole. But when you get back from Clipper, the complex polygon, holes will be represented in clockwise winding. And so I just detect that there is a clockwise winding, and I delete it out of there so that it doesn't cause any trouble. So in case you're wondering like why things work the way they do when you try to make like some kind of complicated shape. So you can see if there's still a little sliver of way to get in there, you can do so, but as soon as you close it off, it just disappears. But yeah, again, well, let me reset it. Yeah, I think that was 3. So go between everything. And just because it sort of looks right doesn't necessarily mean that it is, so it is worthwhile to confirm you truly have connectivity between, because, for instance, say So like this area right here with these two blue waypoints, well, there's a little tiny edge between them, or at least there should be. So we've already walked through, so we know that there is one in my example here. But if you had a bug, there might be a missing edge right there. And so if let's say the agent was like in the neighborhood, like right there, and you clicked over here, and the agent chooses with A star to go all the way around the long way, then you can pretty safely assume that you're missing an edge in there. And I'll show you a way to look more closely at that, not using the play window or the game window, but instead the editor window. All right, so where were we? We're on, let's see, 3. Yeah, that's scene 3. All right, 4. So here is 4 and 5. And my, I don't know, well, it will depend on your computer exactly how fast it'll take. But even so, I'm guessing my code's probably running faster, and that is because I'm caching in a dictionary all of the calculations that are involved in the brute force triangulation. So that really helps a lot on performance. So like if I load fresh, that yeah, it's taken about a half a second. This I think is the most difficult scene. I believe previously when I didn't cache everything, this took a few seconds, but now I'm at a half a second. So don't worry if yours is taking a few seconds. I think as far as grading, we allow 20 seconds on our grading machines. But if you're not messing with the, if you're not changing the structure of the looping that is suggested in the pseudocode, you shouldn't have a problem. And let's see, we got 6 here. I can walk through there. And there is 7 as well. I think this is the last one. Yeah. Yeah, I can make it all around. You might be wondering exactly what is going on with this blue here. Kind of looks different than the others. Well, it's because this obstacle here is being expanded, but it's trimmed to the expanded world boundary. So that's why it's kind of asymmetric looking. And so this is just the blue expanded of that geometry, but also trimmed to the world. So it's making it look a little weird in this area there. So I think that is it. So I think some people have had problems with the right clicking for incremental, and see how it, if you're not careful and click, it starts rotating. So I need to remove that. That was like a legacy feature from a very early version of this code. And so with a touchpad, it is really easy to move. I think it's a bit easier with a mouse, but it's not really necessary to test the incremental. You just need to be able to see if the agent can walk through. Let me go back, and I'm going to turn off maximize on play and run again. I want to show you a few things that you can do in the scene. So I've got the editor running. So this is the editor. Of course, if I want to click, I still have to click on the game side, but I can view over here as well. And so in like this particular scene, one thing I could do is I can, so a feature of this translucent yellow is that it can help you debug when you're triangulating. If you accidentally have an overlap of triangles, which is, I think it's possible if you mess up in a couple key spots in the algorithm. So I've selected a triangle. See how I've got the orange? So I just clicked a couple times to make sure I selected the right one, and now I change to the move tool. And so I'm moving a triangle, and you're seeing how it really stands out when there's triangle overlap. And you can see it in the game as well. So that's what it looked like in the game view. So that helps you debug if you're having trouble. Of course, if you saw a big black open area like that, like if this triangle was just gone, you'll see that there's a big chunk missing. So that would probably be something that you should be concerned about, and go back and look at your algorithm if you're missing a triangle. So the only place there should not be yellow is, well, within these blue boundaries, which are the obstacles, and then the offset. So I don't draw the offset from the canvas world just to kind of minimize the clutter. But you should just expect there to be the radius offset towards the interior of the space. So the next thing you might be interested in is getting rid of all of your path nodes. I mean, that's certainly, it's good to have them for confirming you're forming the path nodes in the right place. But you might be looking for connectivity all around your obstacles. So if you find the navigation area in the hierarchy, which I've got the window docked over here, if you expand navigation area, you'll see this path node markers group. And if you select that path node markers group, it's basically like an empty game object, which then has had no longer empty because I've added all these waypoints to it. If you just go to the inspector and see the little checkbox there, click it, and that disables that and everything underneath it. So you now see the fully connected white line. So it lets you know got everything connected. See, another thing that I have done before. Let's see, this doesn't really have super skinny. Whoops, clicking in the wrong spot. So if you get some like especially skinny triangles, see if I can manage to get it to make a super skinny one. That might do it. Get rid of those guys. And over here, if I wanted to, if it was skinny enough, I can actually get a hold of those blue lines there. So sometimes you can have them so skinny with just the perfect angles that even those thin lines are getting in your way. So you click enough times and just in the right spot, you can highlight it, and then you could say hide it or delete it. And so there's actually more than one there. I got the next one. So I got rid of all of them. And then you can even like hide certain triangles if that helps to figure out stuff. But basically messing around in the scene view and disabling or deleting things, because it's not going to be a permanent change if you edit during play mode. But that can help with debugging. So yeah, we can see the path around, and that's really a key thing to look for. Yeah, so I'd say the main things in terms of like confirming that everything is working is you're looking for coverage. You want yellow everywhere. You don't want overlaps, and you want to see your any obstacles that are present. You want to see a complete loop around them in some form. So like this is a really wonky looking loop around. And there's some, unfortunately, with the really long skinny triangles, that you don't get the best quality, so you get a much better looking triangulation if you were using like Delaunay. And also, instead of using the triangle centroids as the position for your nodes, if we made more nodes at the midpoint of portal edges, it would be much better quality, and it wouldn't guarantee validity across our triangle or our convex regions, but it would at least guarantee that you wouldn't have a possibility of crossing a border, so like a wall, so you wouldn't cross into where an obstacle is if we were using a different way of setting up the path nodes for our graph. And that's something we went over in the lecture. But so yeah, you will probably see a few examples as the agent's moving around of like clipping corners, just because of the fact that we're placing the points in the center of the triangles, and also the long skinny triangles cause trouble as well. All right, so I think that covers everything for the NavMesh assignment. If you have any further questions, feel free to post on Piazza, and I'll be happy to try to help you out. Hello. In this video, I'm going to give a demonstration of the procedural content generation assignment. So in this assignment, you'll be working with Perlin Noise as a way of creating height map based terrain in Unity. Let me switch over. All right, so this is the project that is on GitHub for the assignment. I believe when you first clone the project and open it, you'll have the same problem as usual of a default scene being there. So you actually need to open the correct scene. I already have it open, but just as a recap, what you want to do is go look in the project view, assets, and then under scenes, open up PCG terrain. That is the starter scene for the project. Now this assignment is unique compared to the other assignments that we have worked on, in that you will not be writing procedural code. Instead, you will be creating a declarative specification for rules that define your terrain. So the terrain is a feature. This is built around a feature that is built into Unity. It's called terrain. And so I've already got in this scene everything set up. It's got this manager, which just handles some basic interactivity for the project, allowing you to, if you run the game, you can fly around. You can also hit escape to quit. The free look camera rig, this is again only when you hit play. A light, and then the most important part is this terrain object here. Now the terrain object, it has a terrain and a terrain collider. These two components you get if you create a Unity built-in terrain. So you can do that if you were starting from scratch, for instance. Let's see if you can right click, create, and then if you picked a terrain, it would make an object just like what you see here, this big rectangular grid. And the game object would include the terrain and terrain collider. It would not have this PCG terrain. So that is the script that's provided for the assignment. But this terrain, normally, without procedural content generation, you manually manipulate the terrain. And you'll see in the component there are some little icons, and you can pick to do things like use a paintbrush and you can paint the terrain. And so you're literally painting changes in height. And certainly that is a viable way to create terrain, but it's also tedious, takes a long time. So it'd be nice if you could just generate the desired sort of terrain you like. I want to go ahead and point out some important features with this terrain object that will be useful for this assignment. So there's a little gear. If you mouse over, the tooltip says terrain settings. So if we do that, we'll expand these settings. And the most important items, I think, near the top under basic terrain, there is a material. If for artistic or aesthetic purposes you want to change the material, you can do so. I've already included in the project a number of different materials. So if you hit the little radar button, it'll bring this up. And there's several in here that aren't really appropriate, but you'll notice like there's these stone patterns. Those are some that I imported. I think there might be one or two others with different names that are in here, but a lot of these other materials come from other assets that are in this particular project. So yeah, I think mainly the stone. I believe if you look under third party in the project view, you'll see that there is, see under free, there's a desert rock, and then I've got the stone textures package. I think those are the main sources that you will be interested in. Let's see. So yeah, that's good for the material. You probably want to stick with the current texture, at least while you're editing. And then when you want to, say, create screenshots, then you might switch the material. It's sometimes hard to see exactly what height map features you're generating when you have a complicated looking material. So the other thing that's useful is if you scroll down to texture resolutions, there's one in particular that you'll probably want to manipulate, and that is this height map resolution. It's got a drop down, and I believe the what is posted on Git will be a 513 by 513 height map. If your computer doesn't perform very well, I recommend dropping to 257. Like if there's just too much lag in terms of the manipulations that you're going to be doing, then try dropping that down. And the rules engine will should recognize the change and update everything. And then when you go to say the point that you've completed your terrain, you might switch to a higher resolution so that you get more detail, like in your screenshots. So when you're done, the way the engine works is that it only processes when there are changes to the rules. So once it's done processing, then everything's on the GPU in terms of load, so the number of triangles, and I figure most people can easily handle a higher setting. The one downside in terms of editing when you have a lower resolution height map is that if you have really high frequency noise to create, like, say, fine grained texture, which we'll be learning about shortly, how to do that. But it won't show up necessarily in a low resolution height map. So some of the finer grained details will not show up unless you have a higher resolution height map. So there is a trade-off there in terms of editing. I'm going to leave it at the 513 by 513. And by the way, it has the extra, the +1 past the square power of 2 texture dimensions, because the height map, the way the height map values fall relative to the graphics texture, so they have to add this one extra unit in order to align properly with, and then with the tiling of the textures, it just works out where they need to have that extra unit. I don't think you'll necessarily need to change anything else unless you're just trying to get better lighting, or something more related to the way it renders. You don't really even need the terrain collider because we're not using it for gameplay. But yeah, other than that, you can pretty much ignore the terrain. Again, that is a Unity provided component. And so you'll mainly be using this PCG terrain. All right, so I'll talk about this now. So you do have the, excuse me, you do have the source code for all of this, by the way. So if you're trying to figure out exactly how something is working. But this object or component, it allows you to control and constrain the way that noise is generated. So we're leveraging something called Perlin noise. And Perlin noise is a type of gradient noise. That means that it's not like white noise where you have information at all frequencies. Instead, it's limited to a certain range, and there's a smooth gradient, certain range of frequencies, and there's a smooth gradient between the different values. And so this is really nice for creating natural looking features derived from a random source. So I'll show you a little bit of what this can do. So the simplest thing is that the PCG terrain component can request noise from a Perlin noise API, and then we can control it. And so the main values that you'll be using, there's one called a Perlin scalar. Hopefully you can see that in the video here. So the Perlin scalar, that is, you can think of as like a zoom level on the noise. And then there's this max value. The max value controls how strong the contribution of the noise is. So if I move the scalar around, nothing happens because the max value is currently at 0. But if I bring the max value up, you can see so the Perlin scalar at 0, it's like infinitely zoomed in to the point that there's no noise source. But you can see I can move from 0 to 1. This is the full range of Unity's terrain. It has a normalized value 0 to 1 height. So that's the maximum range of height values that you can set. So the terrain height map is simply a 2D array. It's kind of like a texture, except the values of the pixels are the heights. And so this terrain is made up of lots of little triangles. We're just not seeing the triangles because all the heights are the same currently. But let me put it at, say, halfway. And then I'll start to play with the Perlin scalar. And so you don't have to move it very far, and you'll start to see that we're adding in, we're basically zooming in on a pre-computed texture. And of course, if I keep pushing it, it'll look more and more like static. But if we're on a lower level, we have these nice smooth transitions between the two. And now if I play with the max value, you can see these changes. So what's happening under the hood is that we're calling upon a Perlin noise generating function based on offsets that are relative to the 2D coordinates in the control texture. So the terrain, whatever the terrain dimensions are, get replicated to an array of values in this particular component, this PCG terrain. And then we parse through or loop through each of the pixels, and then we do a relative offset into what the Perlin noise generating function gives. And that's controlled by this Perlin scalar, how far zoomed in we are. So at a high level, it's really pretty simple what is going on. And so right away we can get some terrain that looks somewhat interesting, maybe like sand dunes. And the other thing we can do is we can control like a fixed offset for the terrain generation. And so if I pick one of these dimensions here, and you'll notice I have X offset and Y offset, and these have 1,000, 100, 10, and 1. So this is basically the reason why there's all these different levels is so that you can control how far the slider, how big of an effect the slider has. It unfortunately has a really tiny resolution relative to the full size of the editor. So if I had a really large range of offsets and you try to slide it, you wouldn't be able to move in tiny increments if you wanted to. So if you want tiny increments, you can pick X offset 1, and then you can move that way. So right, you can immediately see the changes update on the screen. And so this shows how the terrain might be generated if we expanded a bigger than this small patch of terrain we had. So this could continue on and on forever. Eventually it loops, or repeats rather. But you can see that it has a nice smooth transition through different values. And if I want to go further, I could pick a different value, and you can see how it moves a lot quicker with a different range of values. So these are just taken as a sum together. The offset 1,000, 100, 10, and 1 are all added up, but you can tweak them as you see fit. The same with the Y, it just moves in the other direction. And Z is, so this particular implementation of Perlin noise, it also has a Z offset. So you can think of it as a 3D space. I don't have all the offsets there for the Z offset, but I left, even though we're don't really need this feature, this just is another way to add some variation if you choose. And so yeah, it's just got the one slider value, but this one makes less sense, at least in terms of, say, tiling terrain. You would probably have the same Z offset for everything. So that covers most everything you need to know about having a single node of the terrain generation. So it's all of the features related to a single node are really these first parameters down to this drop-down gen noise type. Now, I guess there's one other thing I haven't mentioned, and that is you can filter your Perlin noise through a mapping curve. And so if I select that now, this introduces some overhead, extra overhead. And I'll probably see it's updating more slowly now is my guess. I can't tell too much. But what that is doing, when you select Perlin noise with mapping curve, you can apply a function to the evaluation of your noise. So you as an input, you provide an XY coordinate. So these X offset and Y offset, and also the Z offset. That is given to the Perlin noise generation function with the scalar, and then it spits out a value, and that's multiplied by the max value to set how strong it is. But before it gets applied to the terrain, you can send it through this function. And so there is, this is actually Unity's curve editor. And the curve editor lets you define a function shape. So you could remap, say, a Y value that's returned, or a Perlin noise value that's returned is an input along the x-axis, and we can map it to a Y value here. So we could do something like that, and you can see the change hopefully in the video behind. We can manipulate exactly how the noise is is generated. So this gives us a lot more flexibility in how we can generate even within one node. So if you are going to manipulate the function, this gen noise curve here, just be aware that it will have no effect unless you change this drop down from Perlenoise to Perlenoise with mapping curve. And the reason why it doesn't just always use the curve is because of the computational overhead. So you have to really want it to, and then turn it on. You could also set to none. That's really only useful for when we talk about adding hierarchies to the rules. So generally you'll have the Perlenoise on and you'll have some settings set here. All right, so next up we can consider creating a hierarchy. So with Perlenoise, you can actually layer Perlenoise on top of Perlenoise and create even cooler sorts of PCG effects. And typically how this is done is you have, say, Perlenoise at a base level, base frequency, and then you apply octave of the Perlenoise with diminished amplitude. But this particular tool, it doesn't impose any constraints on like definitely having the octave multiples of the frequency. So it's just up to you to set it, and also there's no constraint on the amplitude either. So if you're already familiar with Unity, you probably normally think of creating objects by using, like, say, right-clicking and then doing create empty or create whatever you want under each object in the terrain. But for convenience, and actually highly recommended that you use the automation provided to create new nodes because there's a lot of things that need to be set up correctly. So if you want to add another node and so that you can create layered Perlenoise effects, use the create button down here at the bottom. So if you scroll, if you have the terrain object highlighted, scroll to the bottom, click add child PCG terrain node. It will create this new node that's added here. I recommend you change the name to explain what it is you're doing. So you want to change it in this config region here, not up here. So this is normally where you have the name of a Unity object, but instead the way the script works is that this always overrides that, and they're synchronized though. So let's say I want to call this terrain detail. I'll call it terrain detail 1, I guess. So you can see that it changed up here. So I can make that change. Now right now the Perlenoise here is very small, so we're not seeing much of an effect. But we can increase the Perlenoise scalar to get a high frequency. Now we can't really tell much at this point because the magnitude or this max value is very high. So if I scale this down, you can then maybe tell that it's layered on top of the noise at the root level, which is this object. So this object called terrain has a Perlin scalar at 6.1 and the max value of 0.225. Actually, let me crank this up a bit. All right, and then this terrain detail 1 has 30 for the noise type, so much higher frequency is the resulting effect. But I cranked down the max value a good bit, so you can see that it's additive with its parent. And I can move around here, give you a look at the terrain. So you can see now it's got kind of like looks like, I don't know, maybe a bumpy surface on an asteroid or something like that. And and then we can, with the terrain detail, of course, we can play with the offsets. So I can slide things around. You can see that it changes the texture on top of that lower frequency. And then one cool thing you can do is, if we go back to the parent, so these offsets are, the hierarchy is designed in such a way that the offsets build on top of each other, so you can have everything move together. So see how it looks like we're doing like a flyover now. So the high frequencies are locked to the low frequency features of the terrain. And we can even go further, so we could add some even higher frequency details on top of that terrain. So I'll go to add a child again. So I've selected the second level terrain detail 1, and I'm going to click add child PCG terrain node, which is at the bottom of the PCG terrain script component. And I'll call this, give it a name, and we'll call that terrain detail 2. And then I will pick an even higher frequency, and then pull down this max value. So you can see, I think we're reaching the limits of the texture resolution, but you can see that it's now evaluating that. And if I go back to the root and play with the offset, you can see it all slides along, but now it's computing slower. The frame rate of the changes is dropping. Let me see, hopefully this works. I'll go try to change the resolution and see if there's any detail that pops up. Of course, when I change the resolution of the texture, the frame rate is going to drop even lower for any changes made. Okay, that actually didn't have much of a change, but maybe if I go higher frequency here. Yeah, there you go. So it can get really bumpy, but it's kind of not super interactive. But this is effective with this particular resolution. All right. So I think that covers the basics of how to create a hierarchy. Well, actually, I forgot to mention these drop downs. So with these drop downs, once you have a hierarchy, there's a way that the nodes are parsed. So the first step is the noise is generated for a node, but then that noise that's generated can be processed by a child. So for instance, terrain detail 1 can manipulate its parent's noise. So there's a recursive call, and then the child has an opportunity to manipulate that noise. And so there's two parts to that cycle. One is that the parent can be reinterpreted. So normally you probably want to just do a pass-through. So that's just taking the values of the height map values as provided by the parent. And then there's a combination type. And so this means, like, for whatever the child node generates for its own noise, how does that get combined with the parent? And so most of the time you probably want to add and just pass through the parent and add to it. But you could choose to do these other things, like maybe apply a custom function. There's this trapezoid function and a mapping curve function. You can also take the complement of the parent or just zero out the parent. And then there's also this image processing. So I'm going to save that for a more advanced video. But then the combination type, there's add, subtract, reverse the order of subtraction, multiply, minimum, maximum, and then there's these different normalize, and then there's replace. And so these allow you to control the way in which you add together. So probably subtract will be popular to use. So let me switch to a lower node. So we might subtract, and now in this case, just the nature of the details, like the texture doesn't look any different, but it did drop in height when that was applied. Let's switch it back to add. You can also, there is a possibility that you can run out of resolution, which you might have thought of when I told you that terrain can only have a value from 0 to 1. Let me just go ahead and cause that to happen. So this terrain detail 2, if I generate a really high value, I should hopefully clip. Oh, it is clipping, but actually it's so high frequency that it's hard to tell. Let me do the other node. So I'm switching to terrain detail 1, and then let me try increasing now. All right, so now you can see the clipping a lot easier. Oops. So see those little flat plateaus there? So that is where we clipped. But if I changed add to normalize from parent to top, then what happens is that it's figuring out, it's taking the generated value, this child node is generated noise, and it's remapping that to whatever the peak was from the parent up to the max range, which is 1, or the top. I call that top, but that just means value of 1. So it just does like a linear interpolation from wherever the parent value currently is up to the top, and that's to avoid this node causing clipping. And actually, I probably still have a little bit of clipping if this terrain detail 2 happens to add on top of the normalized value from this node. So you could also put normalized from parent to top here as well, I believe. And you can see that they shrunk a little bit, and so all of the none of these nodes should be clipping because that is used. So if you're having clipping problems, you might want to switch to that. So again, the processing that takes place is that each node generates its noise, but it has to first check recursively if the child node manipulates it in some way. And then if there are no children, it just, of course, uses the noise it generated. If there are children, then it takes the sum of all the children generated values, which take as inputs the parent noise. Then the node in question is actually figuring out its own contribution to children. So of course, if to parent. Of course, if it's the root, the contribution to parent is there's nothing there to do because it is at the top level. But any other node will generate its own noise, figure out the contribution of children, and then relative to the parent, that particular node will figure out if it's processing the parent, like manipulating in any way. Usually it's passing the data through, and then it's combining with the parent, and then that gets returned to the parent. So it's a bit confusing at first because of this recursive logic here, but it ends up being a pretty powerful approach to working with it. You have all the code for this, so if you're curious, you can check out the code. Most everything that's interesting is in PCG terrain. So the highlights are, there is apply Perlin noise. So this is the actual method that generates the Perlin noise and applies it to an array. And these, when possible, everything is cached and reused so that it doesn't have to recalculate everything. So the logic for generating the raw noise, and then there is this process function. This does the recursive logic. And so if you check it out, you'll see that there's the first stage of generating the noise. So this is the node in question's contribution to noise, which here's the call, apply Perlin noise. So that generates that texture. Then if there are children, this next phase here, it'll call each of the children. So the child process. And so the child gets to generate its own noise. And then after all those contributions are added together, so just adding the different generated array values, then there is the processing of the parent. So if there was a parent, then it gets processed. Again, it's most likely going to be passed through, but there are other scenarios where you do differently. And then after the parent is processed, it gets combined. And so you see there's these very simple operations like add. So the parent matrix or array gets added with the locally generated noise, which might have been influenced by children if there were children. And then it gets returned, and then if it's the root node, it gets applied towards the terrain height map. So the root being here, it would just apply it to the terrain. So so that we now have a basic terrain. Let me bring this back down to a lower level. Oh, I need to adjust this one. Bring this back down. So here is our terrain. Now, if we want to save this is actually using a feature called these scriptable objects in Unity. And the particular object it's saving to is this PCG terrain data. And that happens to be under student work, already made for you. So this PCG terrain data is here. And we can save it. So you'll see there's some settings down here at the bottom. So I've got the root object selected. These will only show up in the root, the saving and loading. But we can click save. And by the way, be careful with these. There's no user-friendly error checking here. So if I click save, it will have saved to the scriptable object. Now you can click it and look at it in the inspector. And we'll see that there's the terrain object, terrain detail 1, and terrain detail 2. So those are all of the objects we expected with their various settings. And then that file, let's see if I can show this to you. Just a second. All right, so like this is an Explorer. I just did show an Explorer, and so that's the file. And I opened it, and we can see what it looks like. So this is YAML file format, and we can just confirm that it's got everything saved. So we can see that there's the terrain object, terrain detail 1, and terrain detail 2 with all the settings that we expect. And of course, we could maybe check some of these values if we wanted to confirm. But that's the only asset that you have to submit when you complete your work will be that file, and then of course your screenshots that you take. But you can also, I'll make a separate video for creating new terrains or perhaps swapping. Like if you want to make multiple versions of terrain, you can make multiple of these scriptable objects. But I'll make a separate video for that. So this covers the very basics. Now that what I've explained so far isn't a complete description on how to do everything needed for the assignment, but it should hopefully at least get you to the point where you understand some of the basics and can start playing around. So I'll make some more advanced videos as well. Hello. In this video, I'm going to go through some advanced features of the procedural content generation starter project. This will help with completing your homework assignment. So I'll start by showing you this example scene. This doesn't quite meet the requirements of the assignment, but it does demonstrate some of the advanced features. So I already spent some time on designing this one. You can see there's clearly mountains, and then outside of the mountains there are these hilly areas with what look like maybe meteor strikes or some other type of holes in the ground, and there's a few little spots with stones sticking up out of the ground. So these features were all made simply by putting constraints on Perlin noise. And so there is a hierarchy, and I've got a number of different nodes here that you can see. So I'm going to go through some examples of how to do this. So what I'm going to do is I'm going to switch to a blank configuration. So what I'm doing is I'm switching to a different config serializable object, and then I'm going to click load. And so this particular one you can see is just the original terrain data. If you want to make new ones, you can do Control D or select from the file menu. It's Command D on a Mac. But you can see I can duplicate these things, and then if I want to switch, I can drag into the config serializable object field and then click load, and it will do what's necessary to load that particular data. So this is helpful if you want to work with different versions. You can switch between them. You want to make sure you remember to hit load to get it to be up to date. And that's because every node has a reference to the config serializable object. So if you swap the root, then you'll actually have a situation where some of the nodes are pointing to different, well, the first node will be pointing to the new file, and all the others will be pointing to an old one. Not to mention that those nodes don't exist most likely in your other save file. So you want to make sure you always immediately hit load after you change where it's pointing, and then it'll synchronize everything. All right, so we're to the starting point of the assignment. You might have some slightly different settings in the config from, at least for what you get from the GitHub. So this, like this max value is probably set to 0. You can see I can move this currently. Oh, and probably the noise type might be on Perlin. So I've switched it to none. And what I'm going to do is I'm going to move this up a bit. And the reason I'm doing this is I don't want the value base level terrain height to be pegged at the lowest level, because then I won't be able to subtract anything away from the terrain. So I want to bring it up a little bit so I have some room to work if I want to carve away from terrain rather than only being additive. The downside is I lose some ability to add. So that's the first thing. I have a gen type of none. So that means the terrain is strictly defined by the max value. And the other settings really don't matter at this point. So you can see I've just got a flat plane. Next thing I want to do is I want to generate some noise that will serve as control for the different regions that I'm going to make. So I'm going to make a new node. So we'll call these regions biomes, even though this isn't, the way I'm going to show you an example, it's not really properly a biome, at least like the way you see it in, say, Minecraft. All right, so I've declared this biomes, and I've got it's set to Perlin noise. I want some really low frequency noise. Now, for the purpose of demonstration, so we can see everything in the same tile, I'm gonna make it a little higher than like so. So if you're making true biomes where you have to say if your character that exists in this world would have to walk a ways before they transition, say from desert to mountain or that sort of thing, you'd probably have an extremely low scalar value. But I'm gonna crank it up a bit, and then so you can see if I move this max value around, I can see different values. So it looks rather extreme at a level of say like 1. So I can actually need to bring it down a bit because, like I said before, we have this base level terrain height that is, I currently have it at 0.2. So the range is 0 to 1. Have it at 0.2. So here I need to really keep the max value around 0.8 to ensure that I'm not clipping. Now these values that I'm going to be using are actually going to serve as like a probability of being in a particular biome, which we'll see in a second here. So I've got this noise defined. Then what I'm going to do is I'm going to make a new node under, and I can call this, say, the mountain biome. So I've renamed it. It's definitely very useful to rename. Let's see, this has got some noise here, so you can see it's currently adding with its default value, so I'm just muting it. So we actually don't want to generate any noise. What we're going to do here, so I'm going to set that to none, and I'll just crank this down for now to a max value of 0. So right now it's adding nothing. So here is where we're going to process the parent. So as I said before, this biomes node that we made with Perlin noise, that's really going to tell us the likelihood we're in a particular biome. And I'm going to use the trapezoid function. And so there's two types of ways you can remap values. So there's the trapezoid function and there's the mapping curve. The trapezoid function is, I think, much quicker to work with once you understand how it works. The mapping curve gives better results, but it's slower to process and it's tedious to edit. So what I often do is I quickly rough things out with the trapezoid function, and then I will often later go in and replace the trapezoid function with a mapping curve that has much smoother transitions between areas. So I'm going to set this. In order to use the trapezoid function, we have to have process parent variables. And so I had in mind that there might be lots of different types of parent processing. So there's these parent process variables array. So the trapezoid function takes 4 values. So we'll set the array to 4. Now you only set the x values for the trapezoid function in terms of mapping. There are assumed values for y. So element 0 is anything to the left of this x value would be 0. And then at that value, it's the y value is 0. And then above that, it linearly interpolates between the element 0 x value and the element 1 x value. The element 1 will map to a value of 1, so the y value 1. So you have no control directly over what y values these x values correspond to. It's predefined for you. So Element 0, it corresponds to a y value of 0. Element 1 corresponds to a y value of 1. Element 2, y value of 1, and element 3, y value of 0. So you basically are creating a trapezoidal shape that ramps up from 0 to 1, has a plateau at 1, and then ramps back down from 1 to 0. So we can use that to specify where our mountains are going to be. So again, the biomes is like a probability map, and then we're using that probability map to pick a subset of it with the mapping function, and that's where our mountains are going to be. So I'm going to say that we're going to stay 0 up until, I'll just pick something for now. Let's see. I'll go with 0.5. And then, so that's everything below 0.5 is mapped to 0. And then from 0.5 to 0.6, it's going to map to a 1. And then we'll say we'll go all the way to 1. So we're ramping up from 0.5 to 0.6 and then have a plateau. And so you can actually see the effect here. This is showing where our mountains will be. And actually, I'm going to set this to multiply so we can see, visualize where these mountains are. So that just lets me see where the mountains are. But actually, I'm going to pull this max value down to 0. Now I'm going to, underneath this mountains biome node, I'm going to add a new child node. I'm going to name this mountain base. And I'm going to get some noise of a pretty low frequency. And let's see if I can. Oh, that's actually, I think I just want this to be add. All right, so I've got at least something roughed out that looks like mountains. You can tell there's a bit of awkward shape because of the trapezoid. You can see kind of looks like a tooth more than a mountain. But we could fix that later by smoothing things out, by switching to a curve rather than the trapezoidal shape. All right. And then I could say add another node. Call this mountain detail. Pick some higher frequency. Okay, and I can go back to the mountain biome and play around. See, I can spread out, or I can lower the slope of the trapezoid, and you can see right away it gives a better result here. And then I might want to bring my base down a little bit. That works pretty well. All right, so that gives me at least a starting point for some mountains. I might even just stick with the trapezoid function. If you're satisfied with it, you could just leave it as is. So then what I'm going to do is make a new biome. So as you recall, this one ramps up from 0, starting at 0.45 up to the plateaus of the trapezoid is at 0.6, and then it continues on, and it just has a vertical slope at the end. So I'm going to make a new child node under the biomes. As you recall, biomes is giving me the source like probabilities that I'm leveraging. I'll call this hills biome. And don't need any noise. I want to apply a trapezoid function, and I'm going to multiply, set the max value to 1 for now, just for visualization. I'm going to make 4 variables, and I'm going to go the other way. So what was this again? 4, 5 to 6. So let's go to, let's see, 3 to 0. So what I've done is I've used the other half of the range, or the other side of the range of values. And so right now I've got the max value set at 1. And that just helps me to visualize, well, where are the hills going to be? I'm going to crank that back down to 0 again here in a second. But it looks like it's something I can work with. And I'll certainly have to do a lot of like tweaking to get things just right. It's often tricky to get the transitions to look good, but I have something I can work with at least. So I'm going to add a child node to the hills biome. Call this hills base. And give it a little bit of Perlin noise here. Bring it down a little bit. So that's looking pretty good. You'll notice you can clearly see the effect of the trapezoid function with this kind of odd scalloped look here. And again, that is something we can get rid of, but we can work so much more quickly by defining our mapping with the trapezoid at first, and then I'll show you the curve editing in a second. All right, so that gives us some hills. We might go and play with the particular mapping here. So 0, 0, that means we have a we basically have a vertical slope on the left side of the trapezoid, working our way up in values, and then at 0.3 it ramps down from the plateau all the way to 0 by the time you get to the value 0.5, and it stays 0 from then on. So I could try playing around with these values. See, I'm starting to overlap into the hill area if I go from 0.5 to 0.55, because I know that ramps over. So you get this influence, so like a mixture of the two biomes together if you do that. And if I want a steeper slope, I could say drop from 0.3 to 0.25 and see it's more gradual in that case. So I still have that kind of weird little scalloped area, but already it looks a little better doing that. And let's see, I think next I will show adding some features. Let me add a little bit of hill detail here. I'm going to add another child node. We'll call this hill detail. And this will use Perlin noise to add in, but I only want a little It looks a little bit too stone-like. Let's see if I can make it look a little more like soil. Maybe that'll work. Okay. And then I'm going to add see if I can think where's the best place to add. I guess I'll see if I can add it to hill base. I'm going to add a child here. Bring that down for now. And this, I'll try to make some like little stone type shapes. I'll just name this stones. Now here's the tricky thing. If you want to make stones, let's see. Oh, I think I need to actually, I think I do need the stones under hill detail. So the problem is when a node has children, like Hill's base has hill detail and stones, the issue that I'm having here is that this is Hill's detail is adding to hills, and so stones is also adding to hills, and so it's actually doubling the size of the hills because these two get added, but they already have the contribution of hills. Let's see, I might be able to zero out, oops, not here, in stones, I might be able to zero out the parent. Let's see if that works. Oh, but then, yeah, I don't think that's going to do what I want here. Let's see if I can still add. Oh, yeah, maybe I can go this route. All right, so I've zeroed out the parent so I don't double the parent because Hill's detail is already doing that. So let's see if I can continue with this. So if I want to make stones, well, I probably want the stones pretty small, so you'd expect, well, I turn up the Perlin scalar a lot, and then I would just play with this. And, well, this kind of looks like kind of stony, but they're everywhere. I want them sort of isolated, like stones occasionally in the terrain. And this isn't getting it done. So I actually would probably like to have the stones appear, say, if I can get maybe about as often as these peaks that you see here. Maybe I would like there to be stones there, but you can see there's this big gradient buildup, and it looks like I just have more mountains. So mountains with mountains instead of the nice little stones. That would be ideal. So what I can do is I can use a curve. So I'm going to switch the Perlin noise to Perlin noise with mapping curve. And then I'm going to select the tool to control the gen noise curve. Click that. It's popped up on my other screen. And so I can manipulate this curve. Right now it's just mapping 1 to 1. So this effectively has no effect on it currently, but you can see I can play around with this and get different shapes. So I can add different keys, and the keys I'm getting with a right click. Then I can play with the normals. So you can see I'm already getting some like interesting shapes here. Let's see, I'll just jump to this curve, which is a little closer. You can bookmark previous curves you made, which is helpful. So let's see if I can manage to get something. So really what I'm trying to do here is I want to ignore any Perlin noise below a certain threshold. And So you can, if you're looking at the map behind the curve editing I'm doing, you can see I've got some kind of stalactite looking things. So I can play with this with enough time, but you probably don't want to watch me spend too much time on that. But the idea is I want to just isolate the highest values in my generated noise, and that's going to be my stone shapes. And then if I want them to be smaller, I can do so. And I can get fancier in this curve if I wanted to, say, let's see. I want to add like a little weird blip around. So if you want to get like a depression, you can do some interesting things. So get a little like a sunken area around. Make it a little deeper, so I'm bringing up to a base level. So I've got that sunken area. You can see it here in the map. So there's a little stone and then like some type of erosion around where they are. And I could actually maybe do subtract instead. Now I've got these kind of cool looking pockmarks on the terrain. Of course, you can do all sorts of function shapes to get interesting effects that you might like. But you can see how they're now spread out nicely, which is a trick you can do for is kind of a way that you can place features periodically. And you'll notice that these features, because they're under the hills biome, they're only on the hills and not on the mountains. If I go to the terrain here, which is the root level node, I can now slide around. You can see what everything looks like far away from where we started. You can see it repeats. It just goes on and on. It takes a good bit of effort to get the tiling. But yeah, there's lots of places that, say, your game player could explore. But this should give you an idea of how you can tackle this task of designing rules that have these different areas. And so you can do similar things. You can make canyons, all just by using the mapping function. Say if you make a biome, you can identify a range to be canyons, and then you can choose to do add or subtract, and some of the other combinations. You can make, say, features that are just like at the top of your mountains. So there's a lot you can do to create terrain, but hopefully, having seen these functions that will help you out. I guess one thing I didn't show was switching from a trapezoid function to a curve. So we still have a slight bit of an artifact in the hills. Maybe I'll show that real quick. So as you recall, the hills biome has got this trapezoid function. So it's all flat up to 0.25, and then, it's all flat at 0.25, but that's at value of 1. So the hill is fully engaged from 0 up to 0.25, and then it ramps down to 0.5. So I could try to make that shape. Go ahead and switch to a mapping curve. So it's going to suddenly change. So I'm going to go process parent curve. And so I know that it needs to be at 1. so I can get it just right, maybe. Oh, all right. And make this flat. And then this one's going to be 0, but I can't. See if I can remember how to. Well, I'll just zoom it equally here. And I can't see my coordinates. I'll just guess. Get it right. All right, make that flat. And I forgot my values already. So I got to go to 0.25. So I add a key here. So 0.25 to, oops, I put this in the wrong place. And I'll break this so that I can control separately. And then go to 0.5. Add another key. So this, I roughed it out, but you can see that it is smoother now, and I really should probably spend a little more time on it, you know, if I was trying to refine it, but just for this video, I'll end that there. But you can see it is a little tedious to edit the curve, but you can see now that the hills look a little better. It doesn't have that artifact from the linear interpolation of the trapezoid. Now with the nonlinear curve, it looks a little better. I could do the same thing with the mountains. Probably could make those nicer. Some other things I could look to try are make more overlap in these transitions, have a more like graceful or gradual change in the transition, which I didn't bother with here, just to make things distinct for the example. But yeah, hopefully that shows you enough to begin to understand the tool and how to define your rules to create your own procedurally generated terrain.